Hello everyone, welcome to Mutlu Learning Hub. Today we are exploring linear regression, a fundamental technique that helps us discover patterns in data. Today we'll focus on simple linear regression, so we'll work with a single input variable. For example, we might want to predict a student's exam score from the number of hours they studied, or a house price from its size. Linear regression helps us uncover patterns in these inputs and make predictions. Let's take a closer look in the data. On the left, we have a sample data set. Each row shows how many hours a student studied and what score they received on the exam. We label these as xi for the input and yi for the output. Altogether, we have m observations. In the matrix form, we collect all inputs into x and all the outputs into y. On the left, we can visualize these pairs in a scatter plot. Each dot represents one student, their study hours on the x-axis and their exam score on the y-axis. We can already see a general trend here. Students who study more tend to get higher scores. Our goal is to find a function f that captures the relationship between input x and output y. We can represent this relationship with the equation. Here, fx is the systematic trend in the data, epsilon is the random noise or error, and our task is to find best possible f that explains y. For example, given a new input x new, we can estimate its output, the predicted value of y. We also denote it by y hat. That's the power of modeling, turning data into a function we can use to predict and understand future outcomes. Looking at our data, we can already notice a clear pattern. As study hours increase, exam scores also tend to go up. This suggests there is a linear relationship between the two variables. That means y, the exam score, changes at a roughly constant rate with x, the number of study hours, so a straight line can capture this trend quite well. We can model this relationship mathematically with this formula. Here, beta 0 is the intercept. The predicted exam score when the student doesn't study at all, which means when x is 0, we get the beta 0. And beta 1 is the slope. It tells us how much the exam score increases for each additional hours of study. On the right, you can see how the line fits the data points. It captures the general upward trend in the scatter plot. Next, we'll talk about how to find the best possible line that fits the data. Let's begin with a simple idea. We want to model the relationship between study hours and exam scores with a straight line. Something like this, y equals beta 0, beta 1 x, and I will denote this function as f beta x. At first, we don't know the right parameters, so we just start with a random line. Then for each point, we calculate the predicted score, that is y predicted equals to f beta of xi. Let's see it on the graph. For example, for this point, the prediction is here. Next, we measure how well our line fits the data. For each point, we calculate the difference between what the model predicts, which is yi predicted, and the actual value. Let's see it on the graph. For example, for this point, its actual value is here and prediction is here, so the error is this difference. That is our error. As you see it here, some predictions will be above the actual points and some predictions will be below the actual points. So if we just added up the errors, the positive and negative ones would cancel out and we would get something misleadingly close to 0. To fix that, we square the errors. This way, every mistake counts as positive and larger errors are penalized more heavily. It's like saying small misses are okay, but big misses are really bad. Then we sum up all the squared errors. Here is the error, y prediction minus y actual. And then we divide this sum by 2m. And we get what's called the cost function. And our goal is to adjust the line, meaning to tweak the intercept and slope until this cost is as small as possible. Keep adjusting beta 0 and beta 1, recalculating predictions and updating until the cost function stops decreasing. At that point, we found our optimal parameters, and that gives us the final fitted line. So far, we've talked about fitting a line to data, but how can a model actually learn from the best line on its own? That's what we'll explore next. We'll start with the cost function, a way to measure how wrong our current line is. If the line's predictions are far from the actual data, the cost is high. If it's close, the cost is low. Then we'll move to gradient descent, a process where the model automatically adjusts its parameters, that's beta 0 and beta 1, little by little to minimize the cost. Think of it as teaching your model to improve itself, one small step at a time. Thanks for watching. I hope you enjoyed the video and learned something new. Keep exploring, keep learning, and see you next time.